Good morning, everyone, and welcome to another webinar in the Industrial Heating Equipment Association's series on sustainability and decarbonization. My name is Brian Kelly, and I am the current president of the IHEA Board of Directors. And on behalf of the association, I want to thank you all for joining us today. We're excited to continue this series on such an important topic for everyone in the industry. Be sure to check out the rest of the IHEA sustainability webinars on the website that have been recorded and are available for viewing from the past. I'd also like to announce that IHEA is launching its 2024 Industrial Heating Decarbonization Summit planned for this September. The purpose of the summit is to forge a sustainable path to decarbonization for the industrial process heating industry. We're finalizing dates and the location now, and we'll send all webinar attendees save the date notice shortly. Information will be posted on IHEA's website at www.ihea.org. I hope all of you will plan to join us on this. Before we get started, I'd like to remind everyone that all attendees are on mute. If you have any questions along the way, if it's pertinent during Jason's discussion, we'll maybe address them then, but type them in the panels or the questions panel, and the speaker will address the questions at the end of the webinar if we don't get to it during the session. All attendees will receive a brief survey after the webinar. We'll only take a few minutes to reply. We really appreciate your feedback as he continues the critical initiative for the industrial heat processing industry on this subject. One last announcement, the webinar is being recorded and will be available in the sustainability area of IHEA's website within the next few days. And you'll receive an email once that link is available. So feel free to share that with colleagues that couldn't make it today. Now I'd like to introduce the presenter for today's webinar. It's titled Introduction to Hydrogen. Jason Safars is a regional sales manager for Carl Dungs Inc. and is based in the Cleveland, Ohio area. He has over 20 years experience in the combustion industry, holding various sales and marketing, management and global key account management and engineering roles and positions throughout the years. In addition, Jason has extensive knowledge of the international safety standards and codes across multiple industries and industrial and commercial processes, and holds committee leadership positions in several industry groups, as well as he is on the IHEA Board of Directors and currently chairs the Safety and Standards Committee. So thank you for being here today, Jason. Take it away.
All right, thanks, Brian. Again, Jason here with Carl Dungs, and we'll be talking about our introduction to hydrogen. And as we get into this, first a little bit about the scope of the content. This is going to be related specific to thermal processing equipment. As we start talking about different uses of fuels and specifically hydrogen, it's such a broad topic that we need to really focus down. So that's really what our focus is going to be today, is just thermal processing equipment, more within the coverage of what IHEA deals with on a day-to-day basis. So today we'll cover a bit of the properties and characteristics of hydrogen, talk about fuel train applications, so its sizing and some of the other content around what are some of the considerations with fuel trains as we start introducing hydrogen into the fuel mix, and then talk about where we stand with these standards and codes as applicable to hydrogen in our furnaces and ovens and fuel trains. Again, this is going to be a general risks related to the properties of gaseous fuel and using it in thermal processing equipment. Really, there's two scopes when we talk about hydrogen as a fuel. There's enriched mixtures, where we're blending in hydrogen into natural gas, and then we've also got 100% pure hydrogen used as a fuel. The disclaimer on this is that everything we're covering today is kind of in a moving state. Aside from the chemistry of it and the physics don't really change, but hydrogen used in thermal processing today and with the standards and codes is evolving. Just for example, when we created this presentation about a year and a half, 2 years ago to today, what we're telling people and what we're seeing in the industry is changing. So pretty much after today, in about 6 months from now, you're going to see some different responses, specifically in the standards and codes sections. Some of the things we are not covering. We're not going to get into fire protection, monitoring of buildings and rooms or other safety type applications and hazardous location requirements. We're not going to talk about generating hydrogen at your facility, using hydrolyzers or storing it. That's a whole another topic on the supply side we may be getting into down the road. We're not going to really cover plant distribution systems. So how do I pipe it through a facility to get to the furnace? We're not going to talk about hydrogen used as an atmosphere for heat treating, specifically like a Class C furnace in NFP 86. That has been around for a while and is a whole kind of separate topic. It's really about using hydrogen as a fuel. We're also going to really stop this presentation from a detailed content point at the inlet to the burner. So we're not really going to get too far into the combustion discussion, impact of hydrogen on burners and furnaces. We're going to pick up that topic on March 28th with the next in this series of Hydrogen Basics, which Brian, who just did the introduction, will be covering that. So definitely, we'd like to see everybody sign back in and continue on with these topics. So jumping into material here, we'll talk about the chemistry side of it and a little bit of the combustion introduction. So things like its definition and some of the characteristics of its flame, its temperature, some of it about its density and heating values, and ultimately its size as related to or comparable to things like natural gas and propane. So for this presentation and in general, when we're talking about using hydrogen as a fuel, we are talking about its use as diatomic hydrogen, which means it's paired with another hydrogen or H2. If you're referring to atomic hydrogen, a single hydrogen atom, that's really when you're looking on the periodic table. It is an unstable atom. It will want to bond with other things. So really for the rest of this presentation and in the future, it's always the conversation about H2 or hydrogen gas. Now, hydrogen, like many other fuels, is colorless, odorless, and tasteless and non-toxic. Typically, we are adding odorants in order for us to be able to smell it. So there is a standard for pure hydrogen to add ethyl isobutyrate, which kind of gives you a rotten cabbage smell. When we get into enriched mixtures, there really isn't a clear standard yet. But typically when you're mixing it with natural gas has mercaptan, which gives you kind of that rotten egg smell or the sulfur smell. But it is an odorant that's allowing you to smell it. The risk here is if you don't have an odorant, you're not going to be able to detect that hydrogen unless you're using something like a combustible gas detector, an analyzer. If it's a leak on piping, you're using soap and water, kind of bubbles to try and find a leak. But in general, odorants are what are going to help us identify it from a smell point. The other thing I did want to mention on this is, in general, we always tell people never trust your nose. So you shouldn't rely on just your nose to find leaks or smell it. There are people out there who are desensitized to mercaptan, can't smell it. I know of one or two people. So again, always rely on combustible gas detectors or some other method, not just your nose, to try and detect leaks. Auto ignition temperature is another factor we want to take a look at. That is basically when I've got a fuel mixed in air at the right ratio, what is the equivalent temperature I need to get the combustion reaction moving forward? So you can see from comparison between hydrogen and natural gas, they're very close in terms of auto ignition temperatures. So that's good news for our burners and our systems where we don't have to do much different in terms of trying to get the reaction to be started. In terms of the flammability range, we talk about percent of gas in volume of air. And that's what these percentages are showing. For natural gas, we have about 5 to 15% gas by volume in air to get it to react and have a flame. You can see hydrogen has a much greater range, especially on the upper flammability limit, up to 75%, which creates a couple different hazards for us, where, from a little bit of hydrogen mixed in air to quite a bit, I can still get a flame to occur or get the combustion process to start. So because of that, the NFPA has designated that hydrogen has one of its highest ratings as a 4. And for those of you not familiar, this kind of little symbol here is one of their hazard classification symbols. So the red indicates a level of fire hazard, the blue is your health hazard, yellow is its reactivity, and the white square would be for specific hazards such as, don't use water with it, it's an oxidizer, it's an acid, it's corrosive. But the rating system is 0 to 4 in the colored areas, with 4 being the highest risk. In terms of flame color, hydrogen will present itself differently than natural gas and propane and some other fuels. In general, when I'm burning pure hydrogen, it's really going to have almost no color or nearly invisible flame color. In this situation, or this example we have here, this is a sealed combustion airflow burner. On the left, you see 100% natural gas. On the right is 100% hydrogen system. Most of the, coloration you see, especially the yellows and the reds, are because of some of the other stuff in the combustion air that's coming along. But you will see a much different type of flame profile depending on the burner as well of what you see in terms of the flame. Here's another example. And again, this is comparing 100% hydrogen to natural gas on the left, where that flame of hydrogen becomes much paler blue. You have some reds in it, a lot more luminosity, or the luminosity is decreased, so you're not seeing as much. On the right side is a comparison of almost like a kind of a Bunsen burner of a hydrogen flame to a propane flame. And you can see again, propane provides a lot more luminosity, a lot more visible aspects to the flame. So these are all things that get taken into consideration a little later as we start getting into this next presentation on burning hydrogen. Thanks to Honeywell Thermal System guys, they did some videos on an Eclipse thermojet burner. And this is a little video that shows just some of the fuel switching, what happens when I go from 100% natural gas to 100% hydrogen and backwards again. So getting this moving forward, you'll just see steps. And this, by the way, this video is kind of a fast forwarded video. So it goes a little bit faster in terms of the blending here. We would go in reality a lot slower. But you can see the flame envelope starts reducing down, less visible flame coming out of it. Your flame color starts changing as we move to 100% hydrogen. Good news is that, all of the burner OEMs out there, most of them who are in the industrial process arena, have tested hydrogen, know how to burn it. So it's not like this is a completely wide open field that there's no experience out there. But again, the biggest takeaway from this one is make sure that when you are looking at hydrogen to bring into your facility to run in a furnace, that you're working not only with your furnace OEM, but also with the burner OEMs quite closely to make sure we do it safely and effectively. Flame speed and flame temperature are two other considerations. Natural gas has about a 1.3 foot per second flame speed. And when you're looking at a burner or a flame, the flame's actually trying to travel back to its source. So it's going back towards the burner. So in the pictures here, it's actually trying to go down into the burner nozzle. Hydrogen has a much higher flame speed, so there needs to be consideration for that in the design of the burner and the system. It means that it has a higher rate of flashback or a higher risk of flashback So again, something to consider and making sure you employ or engage the right people when you're looking at switching over to hydrogen. Flame temperatures are very similar, and that's a adiabatic flame temperature. So we're measuring the temperature of the flame in the core before it starts getting infused with air and some other, losses to the system. So pretty close in terms of flame temperature, not a major difference between the two. One of the things you notice from the pictures as well is that, I mentioned that the flame isn't as luminous when you go to hydrogen. And part of that is it emits much less infrared heat. So the radiation coming off of the hydrogen flame is less than natural gas. There is substantial UV radiation. That's not something we as humans can see or really feel too much, at least not in short-term exposure. So there is a risk when we're looking at hydrogen flames that you don't get that same sensation of the radiation coming off of it. And it could make for people inadvertently getting closer to a flame or maybe not recognizing that there is one when there actually is a flame. So just be cautious and aware of that. That also impacts a bit about what we do with flame detection. So again, hydrogen flames are radiating more of their energy in the UV wavelength, less in IR. So we're going to use typically more of a UV flame detector when we're doing flame detection on burners. Flame rods are also acceptable up to about 90% hydrogen enrichment. Once we get over that 90% threshold, the way a flame rod is working is more about almost like creating a electrical circuit, grounding out a loop. So as you get less of a flame envelope, the reaction of it on a flame rod is less, and they become unreliable, really. So if it's 100% hydrogen system, you're typically only going to be seeing UV scanners used for hydrogen flames. And that picture there that's over on the right is just really showing a hydrogen flame where you can't really see it until it lights the room on fire. So they are pretty invisible when they're pure 100% hydrogen, at least to the naked eye. So heating value and density are two other characteristics that play into really more on the burner sizing or burner considerations and the fuel train sizing. Hydrogen by itself has a heating value that's about 1/3 of that by volume versus natural gas. So natural gas has about 1,000 BTUs per cubic foot versus 325 for hydrogen. And those are, at least in the US, we typically refer to the higher heating value. When you get into Europe and some other places around the world, they'll refer to the lower heating value. So you'll see different BTUs for cubic foot, as well as in different units, more in kilowatts per cubic meter. But that difference between higher and lower heating value is nothing more than the heat of vaporization required for water. So the losses in vaporizing that water vapor that is entrained within the fuels themselves. So a big difference there. The risk when you're comparing just hydrogen to natural gas, obviously, is that because of that lower heating value, I'm going to need a lot more volume to go to the burner in order to get it to still get the same amount of heat into the furnace. Hydrogen is also about 8 times lighter than natural gas. So that also plays in with less dense, needing more volume to go through a fuel train to get to a burner. The good news is if I've got a leak, it's released into the atmosphere. It's typically going to rise and disperse much more rapidly than natural gas. So from a safety standpoint, that's better. Just from a sizing standpoint and comparing the two, there are going to be differences. So the last thing we'll talk about on the properties and characteristics is its molecular diameter. So we're talking in terms of angstroms, and an angstrom is 3.9 times 10 to the minus ninth inch, so pretty small. But in general, hydrogen, H2, has about a width of about 2.1 angstroms versus 4 for natural gas. So it's about half the size of natural gas. That'll play into our conversation about fuel trains and safety shutoff valves and leakage rates. But we don't necessarily always talk about just the size by itself, because when hydrogen and natural gas are in a mixture like that, they tend to vibrate and bounce around. The likelihood of them bouncing into other molecules and interacting with others is called the kinetic diameter. And the kinetic diameter is actually a little bit closer for hydrogen versus natural gas. So it's about 25% kinetic diameter smaller versus natural gas. Again, that plays into more of our conversation about component certification and leakage rates for the fuel train and leakage in general. So that's the basics on just some of the characteristics of hydrogen. Next, we'll talk about starting to apply it to fuel trains. And this, I will tell you, is a little bit more of a gray area, especially as it comes to the standards and codes, but we have learned quite a bit, or we know how to run hydrogen through systems today. So first, we'll start with leakage rates and valve seat leakage. Again, due to its size, it's more susceptible to leaking, to find its way through gaskets and find its way through any pinholes or anything that we might have in the fuel train. And when we're talking about fuel train risks and leakage, it's just a good note to point out, we're not talking about only leakage through a valve seat, like a safety shutoff valve, but we're also talking about the external piping, flanges, gaskets. It's really a holistic look when we say a leak. Normally in practice, if we're finding leaks, be it natural gas or hydrogen, typically it's caused by some human error, some deformed seal or gasket. The valves weren't aligned properly on the gaskets, or the threads weren't done right. Failures of the equipment itself, people hitting fuel trains with lift trucks. That's happened in the past. So if designed right, they are pretty much leak free. So we shouldn't have to worry too much about it. But in terms of some examples, I've got two examples of how hydrogen does create an increased leaking risk. These were done in our lab in Germany, some testing. These are on a 2-inch Dungs MBE dual safety shutoff valve. So it's one of our newer safety shutoff valves, so 2 valves in series. These do have a 15 PSI rating on them. And in this case, we had a leaking valve, and it was just one of them was leaking. If I remember correctly, I think it was the first one, the V1. But what this is showing is at a 15 PSI inlet pressure, how the leakage rate gets affected just by the type of gas we're putting through it. So in the first little chart or graph bar chart out there on the left, we've got basically air at 15 PSI. So internally through the valve, we found that it was leaking at about 3 centimeters per hour, cubic centimeters per hour. And just for point of reference, that's a cc, cubic centimeter per hour, or a cubic centimeter is a cc. A flu shot, if you've gone to get one, on average, those are about a half of cc. So that's like saying we have basically 6 little flu shots leaking past the valve seat per hour. So it's definitely not a lot of volume. The external, so that's in the blue. The orange is external leak tightness. That would be through, threads on plugs, for test ports, through, the fittings. Not exactly sure where that leakage was specifically, but there was some leakage with that valve as well. In terms of if we switch then to methane, and methane has a smaller molecule size. So again, 15 psi methane, it's our second little section. You see that the cc's per hour goes up a little bit, nothing really crazy. Then we go to the third one, which is a enrichment of 80% natural gas and 20% hydrogen. You can see it increases again. And the last one on the far right is showing 100% hydrogen, what the leakage rate is at that 15 psi. So almost double or a little over double that of what air is. So again, molecule size matters, especially on acceptable leakage rates and testing when you're looking at these. But one of the keynotes here is it is pressure dependent, and that'll be a theme that you hear going through a little later in the slide deck here. And this is really a slide to kind of show that example. This is one of our single safety shutoff valves used for high pressure systems. Again, it's a 2-inch. This valve is rated for 100 psi max operating and close-off pressure, and we tested it at 15 and 150 psi, so over its max operating pressure. And you can see with minimum air pressure and minimum 100% hydrogen pressure at 15 psi, there's almost no leaks whatsoever. When we take it in excess of its operating pressure with air, you start getting leaks, and with hydrogen, the leak rate increases quite substantially. So really the message here is when you're designing fuel trains and you're looking at systems in general, and this goes for all fuels, make sure that you're looking at what the max operating or max allowable working pressure is, what it's rated for, and never exceed that pressure. That's why those are out there, and that's why their certifications and their labeling and listing state those items. So vent limiters is another topic to cover. Vent limiters are devices that safely allow you to vent a diaphragm type device without having to pipe it outdoors. So vent limiters restrict your flow on a diaphragm failure to 1 cubic foot per hour or less of fuel. There is some concern for greater leakage rates when using vent limiters and 100% hydrogen. Today, they are certified. If you have a vent limiter and the device is certified for hydrogen, they're okay. For enriched mixtures, they're pretty much theoretically equivalent because it's mostly natural gas anyways. But there is some further discussion going on about vent limiters when used with hydrogen, but we don't really have anything to tell you much more on that at this point in time, other than if I've got a component that's certified or labeled and listed from UL, FM, or TÜV, CSA, and it's certified for 100% hydrogen, it has a vent limiter, you're good to go for today. When in doubt, always ask or talk to your authority having jurisdiction, be that your risk insurer or your local jurisdiction like your state. They will always be able to comment on those topics as well. The last major topic of hydrogen use is material embrittlement. And embrittlement is an interior degradation or deterioration of the material because of a hydrogen reaction to it. This leads to cracks, failures, things you can't see in both metallic and non-metallic parts. So we've got a couple different types of hydrogen embrittlements. There's reaction versions, there's internal pressure-related embrittlement. But in general, it's when the hydrogen H2 breaks apart, which happens often, and you have a lone hydrogen atom by itself that's unstable, it's going to want to try and bond to something. So whether it bonds to iron, it bonds to other things, materials, it'll form what's called hydride, and those hydrides tend to weaken the materials, and deterioration then starts beginning. One of the things that's changed, and I shouldn't say changed, but as we're going through this a bit more, hydrogen embrittlement is really pressure dependent. So the higher the pressure, the increased rate of embrittlement will occur. And when we talk about high pressure, it's typically greater than 66 or 75 psi. Those two numbers really come from um, the standards for the USA and Canada. So depending on where you're looking at, they'll define it as anything over 66 or 75 psi is considered high pressure, where I need to start being concerned about embrittlement. It is a long-term effect, so we're talking years, not days. So nothing's going to happen overnight, usually with embrittlement, and it's again related to all materials that are coming into contact with hydrogen. Here's just two examples of hydrogen embrittlement. Cracks in materials and a flange. Just give you an example of what we're talking about when we say cracks. So as we start talking about sizing of fuel trains, in general, when I'm designing a fuel train for a burner system, it's the same process you go through. So typically, and again, we're not going to get into sizing anything today, but I'm going to usually start with my burner and what its flow rate and what its inlet pressure needs to be, and then work backwards, design, the pressure regulator, 2 safety shut-off valves in series, all the stuff I need to meet code requirements, and then to operate from an air-fuel ratio standpoint, flow control, come up with my pressures, my flows, my velocities, what's acceptable to design the size I need. When I'm comparing just straight up natural gas to hydrogen, again, I need 3 times the amount of volume at the same given pressure. So the example I have here, if I've got a 1,000,000 BTU per hour burner, I'm going to need 1,000 cubic foot of natural gas to get that 1,000,000 BTUs out of it. I need 3,000 CFH of hydrogen. So in general, if I've got equivalent pressures, I'm going to need a larger fuel train. Not too big an issue when I'm talking about new systems, because again, I'm going to design it fresh and new. It's not going to be dependent on any other fuels. I can reduce that pipe size by increasing the pressure to get the flow up and get the velocity, and the velocities will go up as well. But in general, it's going to be a larger pipe size. Again, with all of the discussions about fuel trains, suitability of materials is really number one, and making sure that your declarations and certifications from your device manufacturers, what they're labeled and listed to, whether that's UL or FM or TÜV, cover the fuel you're using at the pressures and temperatures and flows that you're using. Also be concerned with gaskets. We at Dungs use spiral bound gaskets instead of your standard typical gaskets. It compresses a little bit better, makes it harder for the hydrogen to seep out, but getting a 100% hydrogen fuel train today is not a tough thing. Another, just for example, today at Carl Dungs, if you go through our literature, pretty much all of our devices are certified for hydrogen. The same goes for a lot of other manufacturers. I know the Siemens has hydrogen certifications, Honeywell does. So the equipment's out there and the capability is out there to do it. When I get talking about enriched systems, that's where I'm enriching up to 25% by volume of hydrogen in methane or natural gas. I start talking then about a thing called the WOBE index. And WOBE is basically the interchangeability of fuels. So if I set 2 WOBEs equal to each other, 2 different alternate fuels, I should be able to run that combustion system without people knowing I'm really switching fuels. So what's interesting with this one is even with the lower, higher heating values of hydrogen and lower densities, the WOBE index is pretty much similar. So you can see that even when I'm mixing 20% hydrogen, it's pretty much similar to what natural gas would be in terms of a WOBE index. Just another note I didn't really mention, you'll see the 25% enriched systems is kind of a general line in the sand that we've started seeing. Europe is talking about enriching their natural gas pipelines up to 20% by volume. Some of the other standards and code committees have kind of drawn a line at, well, we'll go from 0 to 25% enrichment. Anything over that is kind of going into different buckets for consideration. But one note on here, I added propane in. So propane gas has 2.5 times the BTUs and a much higher density than natural gas or hydrogen. You can see the WOBE is a higher number. If you've ever done a design or you've ever looked at a propane backup system to natural gas, where you've got a propane tank, a vaporizer, and a blender that's blending air in to the propane gas, the whole intent of that blender is to drop the WOBE number down to get it equivalent, where you can switch back and forth between natural gas and propane air mixture, and the systems should all run the same. So again, in this type of consideration, the fuel train sizing should be pretty much the same. You still want to talk about suitability of your materials. Again, certifications, making sure that the devices, safety shutoff valves, pressure switches, manual valves are all certified to use either enriched hydrogen or up to 100% hydrogen. So that's all we're going to cover with the fuel trains. The last piece here is what we know today about the different codes and standards that are out there. And again, this is specific to the thermal processing industry. So starting with storage, there are already standards out there that have been created and have been existing for quite some time. The use of hydrogen in industry is not new. You know, people use it for heat treating. Steel plants, petrochemical plants have been using hydrogen for years. So there are standards out there. 29 CFR 1910 Code of Federal Regulations is for 100% hydrogen storage systems. You've got the ASME Boiler and Pressure Vessel Code that dives into hydrogen storage. Canadian Gas Association has one, as well as NFPA 50A is for storage of hydrogen systems at consumer sites. As I get into fuel piping, that's the distribution system between the storage and my furnace or oven. The ASME power piping sections 3112 and 31.3 will cover the 100% hydrogen and enriched mixtures today. Normally when we're talking thermal processing and natural gas, the National Fuel Gas Code, NFPA 54, is the one we go to. Today it does not address anything hydrogen or anything about enriched mixtures of hydrogen in natural gas. I'm pretty sure they're working on it. There may be some changes coming, but there's nothing really to report, at least during this webinar today. The key thing I do want to mention for any type of fuel piping distribution system, whether 54 covers hydrogen or not specifically, it still should be looked at in terms of if I'm installing new piping, I'm modifying piping, there is procedures and requirements for proper isolation, purging of the line for both getting air out of it, introducing your fuel for the first time with using nitrogen as your purge gas. There's pressure testing requirements. NFPA 56 is for purging and cleaning of high pressure systems, in this case over 125 PSI. But always refer back to those if you are getting hydrogen brought into your site as a fuel, because there are some risks associated with bringing that fuel online. In terms of buildings and rooms, you know, there are gaps right now for mixtures that are out there. NFPA 2 is our Hydrogen Technologies Code, and that's on the 23 edition. It does cover generation, installation, and storage, use and handling for greater than 95% by volume. It today does not cover enriched mixtures. However, there are proposals existing today for expanding that scope to include combustion fuel mixtures of up to 25%. It probably should be a greater sign there, but and that includes specifics about combustion air ventilation in the rooms, gas detection systems, in situ type gas detection systems, emergency shutoffs, getting into fuel trains, just some additional scope that they're looking to expand into. So down the road, may have more to report on that as that progresses. When I get to my thermal processing equipment, so my furnaces and ovens are going to be covered by NFPA 86. 87 is going to be for my thermal fluid heaters. Again, that's a kind of different type of thermal processing equipment. But you're going to focus, or the fuel trains and the burners and all that are really going to be covered under those two standards for your furnaces, ovens, and thermal fluid heaters. Looking elsewhere within a facility, residential, light commercial appliances, air heaters, there are ANSI standards. Folks are working on that as well to introduce language and requirements for covering systems up to 25% of hydrogen enrichment. The key is here that, again, standards exist, fuel train requirements exist today. Even if they don't say hydrogen, they're still your best place to go to look for information or make sure you're designing your system safely. Again, there's gaps in these standards. Everybody is starting to work on them. Typically, everyone's starting again at that 25% enrichment or less. Some of them are going up to the 100% hydrogen, but things are changing relatively rapidly in the standards fields. One other note I'll mention on this is that, when we're talking about standards and codes, they're typically retroactive, meaning something happened or we learned something in the field and then they change. They're not necessarily very forward-looking as a prescriptive standard. So they are a little bit behind always in terms of, addressing new technologies and addressing things that are out there in the field. So expect more to change on all these standards in the coming years. Now, an example is NFPA 86 did recently change. We are now on the 2023 edition, and they have included the words hydrogen gas and hydrogen gas mixtures in the scope for acceptable fuel gases. This is the only reference to hydrogen as a fuel in NFPA 86. So while it's an acceptable fuel, it isn't specifically addressed for any other additional safety requirements other than what's already out there for gas trains and safety systems in the appropriate sections, specifically here in section 6.2 for gas trains. So there'll probably be more coming on that as the committees work through things, but again, that's the only place it's referenced as a fuel. It does show up the word hydrogen in the Class C section for atmospheres, for heat treating furnaces, but again, that's been there for years. So we're talking a little different scope. Lastly, then diving down a little deeper, when I get to safety shutoff valves, pressure switches, pressure regulators, all that, and I'm talking about labeled and listed devices, there are standards out there that cover hydrogen already. So for example, UL 429 is for safety shutoff valves. It already had full coverage for hydrogen. So again, when you look at a Dungs safety shutoff valve, we've had it tested and it's capable of doing up to 100% hydrogen as a fuel gas. So again, other ones, using an example of our company since I know it the best, but a lot of other people have these same certifications. So componentry is out there, the ability to build a fuel train is out there. UL 353 is for your limit controls, for example, pressure switches. That also includes up to 100% hydrogen. And just a note that UL 353 is being sunsetted. There's a new standard it's replacing. It's an IEC 6730. And there's -1, -2, depending on what your specific component you're looking to get labeled and listed or certified is. But that is changing, so that title will change down the road here. The one note I did miss on this slide, UL in all their standards really is only concerned about hydrogen embrittlement of the non-metallic parts, especially in valves, only after you exceed 75 psi. So again, embrittlement considerations for fuel trains that we normally see in thermal processing are nowhere near 75 psi. So it's really kind of a moot point at this juncture from a standards and codes perspective. As we dive a little further, like manual valves, piping and fitting, again, ASME covers our piping, fittings, all the pipe nipples, all that good stuff. All your flow control valves, regulators, and manual valves, again, ask about it from the manufacturers, make sure you get their declarations or their certifications. There is still work in progress on some of the higher and medium pressure regulators, and I kind of will draw the line at about anything over 10, 15 PSI regulators. There are some changes coming for hydrogen on that. But other than that, you know, these are just a snapshot of some of the standards that are out there. There definitely are a lot more when you expand out and say, okay, I want a CSA certified device, I want a TÜV certified device, I'm going into Australia and I need to be AGA certified. So this list becomes extremely long, and we're just giving you a sampling of some of them that you should be asking about. So that's our primary coverage for the introduction of hydrogen in the thermal processing. Just a couple quick reminders and review items here. First, remember that flammability range. It is quite wide. It's got the highest hazard classification for NFPA as 4. So again, going from 5 to 75% by volume and air, it'll have a combustible mixture. Watch those open flames. Again, we don't have a lot of infrared coming off of them. They can be closer to the invisible by the naked eye. So you can get a lot closer to them than you think. That lower heating value and lower density increases the need for higher gas pressures and flows to get the same output of a burner. So you're going to see some different sizing in your fuel trains, as well as be considerate of the leakage rates. You know, when you're doing bubble testing, which is an annual requirement per NFP 86, which is testing each of your valve seat leakages, the threshold for an acceptable leakage changes whether it's natural gas or hydrogen. So be aware of that. Embrittlement, again, really 66 to 75 PSI. We're not concerned about it in our fuel trains. Just, again, make sure all of your components are acceptable to be used with hydrogen or are certified to it or labeled and listed. Odorants, you know, ask the question if you're getting hydrogen on site, whether it's got an odorant. And again, some of the codes are changing, so it may include requirements for odorants or combustible gas detectors to be installed where needed. So that's kind of still a little bit of an open issue for thermal processing folks. And last really is our standards and codes coverage. You know, we've been using hydrogen for quite some time, so the storage and piping really is well developed. We've got things to go to reference. As we get into fuel-fired equipment, and ovens, furnaces, there are some gaps. They are being closed as the committees work on them. On the component side, again, you know, things we've got almost all of our stuff certified for hydrogen. So there are some gaps here and there still left on the component side certification. But in general, you've got really good coverage, so we can kind of move forward with using it today. So on that note, we're done with the content. I appreciate the time and everybody's attention during this webinar. And I think we'll open it up for any questions at this point, if there's anything that popped in on the chat.
Thanks, Jason. Yeah, we did. Mr. Rogelio Perez basically asked, so it is safe to take an existing pipe train and enrich up to 25% hydrogen without changes?
So in all these questions, I'm going to give the "it depends" answer, unfortunately.
Yep. Good.
You absolutely want to still evaluate that fuel train. So again, going back to whoever provided the fuel train, or the, like if it's on a furnace or a boiler, going back to the OEM and saying, hey, we've got enrichment coming. Can you take a look at this and make sure that the components, individually, each component's good, the pressures, the flows, the velocities. I would not just start and say, yeah, it's good, because some of the codes are changing. We also don't know how old that fuel train is, right? It may be out of date from a safety standpoint, but any change of fuel or any change of operating parameters does require you to go back through and kind of reevaluate everything. So hopefully that answered that. Anything else to add on that, Brian?
Yeah, that's exactly what I would say, is that, I mean, you as well as a lot of other people, you can walk into a plant now and smell the mercaptan, the natural gas. So if it's leaking on 100% natural gas, it's going to leak on a mixture of gas and hydrogen. So exactly that. It's like you need to evaluate the existing pipe train to make sure it's tight, and evaluate, I mean, honestly, any sealants and components, just like you said. So I agree.
Good question.
There was a question, I did answer it in chat. It said, are you going to talk about hydrogen costs, sources, CO2 impact? And I answered that with that we will address that in our hydrogen basics in March.
Wonderful.
Follow up to the pipe train question is, how does the testing of valve seats change when using hydrogen?
In terms of the physical test that you do, it does not. You're still going to do what's called a bubble test, where you're applying an inlet pressure to a closed valve, taking a tube out of the downstream side where you have some other isolation, and putting it basically in a cup of water and checking for bubbles. The field test is the same. For those of you who are interested to learn about or see an actual procedure, if you have a copy of NFPA 86, I believe in 87 it's in there, in the annex, there are written procedures. For Carl Dungs, we have procedures in all of our documents. I know for Honeywell, you guys, for the Maxon valves, the procedures are very well written. So multiple places you can go to get that procedure. I think I answered that one, correct?
Yep.
Or I fully answered it. Anything else?
Nothing at this point. So, well, and I'll end it with saying thank you for all of you for attending this webinar. We hope you got a lot out of it. Remember to visit the IHEA website at www.ihea.org and click on the sustainability tab on the menu bar for more information on sustainability and decarbonization. And watch for details for the 2024 Industrial Heating Decarbonization Summit coming in September. Watch for the link for the survey, and take a few minutes to share that feedback with us. It's extremely important to us to make sure that we are delivering things that are pertinent and important to you out in the industrial heat processing industry. And have a great day. And again, appreciate your input and time, Jason. And everybody have a great day and a great week.
Good. Thanks, everybody.
Thank you.